Now, for proton, okay, so we are going to look into this proton NMR. Now, for proton NMR, okay, we need to learn, okay, two types, okay, which is going to be the low resolution, okay, and we have learned the high resolution, okay. So we need to remember, okay, before we actually learn about more detail about low resolution and high resolution, okay, we have learned about the different environment, okay. So what are the different environments? So let's look at, okay, if you have CH3, okay, and then you have CH2, and then OH. Okay, so if you have this, okay, we are going to look at the different environment that is going to be formed. So if you look at this hydrogen is bonded to O. So this is one different environment. So if you look at this, okay, this is going to be another different environment because the carbon is bonded to OH and CH3. And okay, this is going to be another one more different environment, which is going to be, it is bonded to 2 hydrogen and CH2OH. Okay, so we have 3 different environment, and if I show this environment, okay, in let's say for example, when I show this, okay, I am going to show that, okay, this particular environment, 3 hydrogen, maybe the peak is going to be 3 times greater than the one that is going to be one environment. And normally they show that, yeah, they show that. Let's say, for example, this is 3 hydrogen. So this one represents to this. And let's say I want to color code, okay, so this one represents 1H, which is this one. And then for hydrogen that is coming from here, then they are going to be from here to here. So 2 hydrogen. So this is going to be, okay, the information that we can get. Okay, and this information, okay, when you are using this NMR, we are going to use TMS, tetramethylsilane. Okay, why we use tetramethylsilane? Because, okay, there are 2 reasons. Okay, tetramethylsilane, all the hydrogen, the proton inside tetramethylsilane, they are all going to give you the same environment. That is going to be a single peak. And then the second reason is tetramethylsilane is inert, yeah, because they are inert, okay, they don't react, okay, with whatever compound that we add, okay, because of that, okay, we use TMS, okay. TMS is going to give you a 0 reference value. So whatever value, let's say from the TMS, let's say TMS is going to be like this, okay, the blue. So this is TMS, for example, 0. Whatever value that actually going to be given by the reading over here, whatever value that is going to be given as a reading over here, it's all going to be referred to 0.0 from TMS. So they call it as what we call as chemical shift. And this chemical shift is going to be measured in ppm. So this is also going to help you about detail, okay, about the molecule. So that is going to be some sort of what we need to know. Okay, but okay, because this is still going to be low resolution, okay, we are not going to have enough information. Like if you have high definition, okay, high resolution, you are going to see more details. Let's actually look at the same compound and see what are the difference that we are going to have. Okay, the same compound, okay, you are going to get similar. Okay, so I will actually select, okay, I'll just copy and paste it over here. Okay, so you are going to get the same situation, but you will get more information in terms of splitting. Okay, why there is going to be splitting is going to happen. Okay, this splitting is going to happen because, okay, the neighboring hydrogen, okay, normally when you have this, the neighboring hydrogen, they are going to have a shielding. Okay, when they have shielding, okay, the electrons will give you the shielding and they will cause some sort of disturbance, okay, in your NMR. Okay, when there is disturbance, okay, there is going to be splitting will occur. Okay, this splitting, okay, can be the disturbance, okay, it depends on the hydrogen atom attached to the adjacent carbon. And the splitting is used this formula n plus 1. Okay, the formula is n plus 1. Okay, like what I explained to you, let's say you have a house and you are going to be the adjacent houses, okay, neighboring houses, there are 2 houses. They are going to, if let's say you put a loud music, okay, and then their neighbors will start to complain, they will go and approach the police officer or the RT, okay, and then 3 people will come in. So that is why the N+1, the 1 is going to be, you can refer the policeman or the RT. So this is N+1. Okay, so this N+1, okay, is going to be very important because, okay, if you look at this particular molecule, okay, I copy this molecule and bring it down. Okay, if you do for this particular molecule over here, okay, what will happen is, okay, if you look at the 3 hydrogen over here, this is the 3 hydrogen, okay, so you see they are going to have the neighbor is 2, okay, so supposed to follow the N+1, which is 2 plus 1, 3, okay, you are going to get a triplet. So this one supposed to show you a triplet. So how do you show a triplet over here? The triplet is going to be, you are going to have something like this. So the way you draw also, it looks a bit funny because they will follow 1 to 1. Okay, it means the one in the middle, okay, is double the size, okay, compared to the one in the to the side. Yeah, so let's look at this, okay, the red color. Okay, if you look at the red color hydrogen, is going to be the neighboring hydrogen. There are 3, so 3 plus 1 is 4. So they supposed to give you quartet. Okay, so quartet, okay, they will follow 1, 2, 2, 1. You can refer from your textbook. So how does it look? Okay, this one I have to erase a bit. Okay, so it will look like this. Okay, 1, 2, 2, 1. So maybe, okay, I erase more. So 1, okay, 1, go up to 2. Okay, 1, 2, 2, 1. Okay, that is how it looks like. And then this one, okay, the one that is going to be attached to O, not only that, the one that is attached to nitrogen, the hydrogen attached to nitrogen, hydrogen attached to O, they are always going to give you a single peak. Okay, why? Okay, why single peak? Because there is no splitting, because, okay, rapid exchange, okay, will happen, okay, between the hydrogen from here, okay, from the OH hydrogen and the NH hydrogen, they are going to be exchanged with the hydrogen from water. Okay, that is going to be, this hydrogen is going to be exchanged. Because of that, there is no splitting. But please take note, okay, if you use, okay, heavy water, D2O, okay, which is going to be hydrogen 2, okay, so this one is the same as H2, okay, O. So it's not H1O, okay, this is H1O. So if you have, okay, like that, what will happen, okay, when there is rapid exchange, this is going to become 2. This is going to become 2 if you follow that. Yeah. So when that happens, okay, the mass number, yeah, the hydrogen now, the mass number is no longer hydrogen 1. So if the mass number is going to be even, yeah, so you are going to have, okay, no peak is observed over here. Because in order to see the NMR spectrum, you must make sure that you use a odd number mass, because that is the one that we can see. If you use something like D2O and so on, you cannot see. Yeah. So this one, okay, if you use, let's say for example, for this molecule, if you mix with D2O, heavy water, okay, this particular peak will go disappear, and you should be able to explain why this disappears. And this is very, very important. Okay, so this is what we have learned until now.